lot of you. Well, welcome. We are working on the territories of the Senchothan-speaking people of the Coast Salish nations. I'm not going to try and list them all because I will pronounce them wrongly, but I'm pleased to say that we are in direct dialogue with them about the future development of this site, which is, I like to add something other than just an acknowledgement because I think it makes it a lot more real. I'm Ben, I'm the chair of the Friends of the DAO, and it's my distinct pleasure to introduce our speakers, and in particular our speaker tonight, who probably needs no introduction to a lot of you, but he's one of our very special people. He's been a stalwart volunteer since he was in high school, which he graduated from last year. He kept us going last summer, and he's keeping us going this summer too. He is the founder of the Oak Bay High School Astronomy Club, and he's been specifically interested in radio astronomy, which he's taking that interest to the UVic physics department for his undergraduate degree, which he's starting shortly. So without further ado, his main subject is the dual dipole radio telescope, and he's going to talk to us a bit about Jupiter, I believe. Yeah. Or one of those planets, you know. Seen one planet, no. Anyway, so here is Evan Warburton.
Perfect. Hello, testing. Hello. Okay, can everyone hear me? Is this good distance away? Okay, perfect. Thank you, Ben, for that lovely introduction. So my name's Evan, and this is my first time giving a presentation up here. I'm usually over in the dome. You might have seen me if you've come up here before for a star party. I will be talking about this project of mine that I began this past year in grade 12. So here is a quick kind of overview about what I'm going to be talking about tonight. So I'm going to begin with an introduction, kind of my background, how I got into astronomy, why I chose this project, how it came to be, what came of it. I'm going to explain the theory behind it, and then what I built to detect these signals, radio signals coming from Jupiter, and the results I gained, what I did with those results, and then the final component of this project, which was being able to bring it to the Canada-wide Science Fair this past May. And that was an incredible experience, and I will elaborate on that further. And at the end, of course, if you guys have questions, please feel free to ask. I love taking questions, and it'll help me cover things that I might have missed. So, I have grown up in Victoria all my life, very lucky to have been living here for 18 years now. I went through public school and just graduated in June from Oak Bay High School. So I'm still kind of recovering from that whole big grad celebration and everything. And I'm very excited to be starting at UVic in the fall in 2 weeks. My goodness, that has come up quickly. I got really into astronomy back during COVID when I was stuck inside all the time in my room doing some homework and got kind of boring. So I started going out on my bike at night. I'd go for bike rides. I'd bike around Oak Bay, and I'd often end up over at Cattle Point, which is a dark sky park. So if you've ever been there at night and it's clear, you might have seen other astronomers there, members of RASC probably. And I would go there all the time, and I just started to look up and stargaze, and it became like my favorite thing to do. And from there, I was like, wow, there is a lot to learn about out there. So I started doing lots of reading, and come grade 12, like Ben mentioned, I created the astronomy club at Oak Bay, and that was a great opportunity for me to just kind of gather my friends and other people in the school who liked astronomy, and we'd go out to Cattle Point and do star parties, just kind of like this, but way fewer people. Yeah. I've been volunteering here since last spring. Just recently this summer I got hired, so that was nice. I get to be up here and actually get paid for it. And if you ask my friends and family, they'll tell you that I do have many other interests besides astronomy, but as of right now, being up here, this is my main focus, and I'm super excited to take it into post-secondary level. So, where this project began, I needed to find a capstone project for graduating from grade 12. And of course, teachers don't like it when you put this off until the last minute. So they got everyone to decide way back in grade 11. And I was, of course, super into astronomy. I was looking at my options, and I found this project that used ham radio, so amateur radio. And basically what it consisted of was detecting the hydrogen line. So the hydrogen line is a radio frequency that you'll find kind of all throughout galaxies, and it's produced by hydrogen atoms. And so they emit radio signals at a very specific frequency of 1.4 gigahertz. And so I did some research into this, and I found that it was totally possible to do this like from your home with an antenna and set this up. And so I reached out to my uncle, who's also a physicist, and he's super into ham radio. And so he actually got me introduced to the whole branch of amateur radio by gifting me a little SDR dongle for my birthday. So SDR stands for software defined radio. And this is kind of the cutting edge technology of amateur radio these days. You can have a little dongle that plugs into your computer, attach it to an antenna, download some software, and you can basically just tap into any frequency of radio signals. So I began there, and I would pick up signals from like downtown Victoria. I was like, wow, this is really cool. How can I take this to like the intergalactic level? And so through my many days of volunteering up here last summer, I was asking around because there were always astronomers and people who'd love to talk about this stuff up here. And I found a gentleman who works at UVic, and he got me started on the Radio Jove project. So this was after I determined the hydrogen line project was a bit unfeasible, didn't really kind of meet all the things that I wanted to complete. And so I started looking into the Radio Jove project. And this project basically consists of many amateur radio astronomers across the world. And they have a website, and they have so much information for people just like me who want to get into this stuff. And the ultimate goal is essentially to build your own radio antenna and collect your own data, and then upload it to one big shared database. And so with all these amateurs working together to collect the data and uploading it, the professionals can then go and take the data and use it in their own research. And the Radio Jove project in particular focuses on a very specific kind of area of astronomy, and that is these radio signals that come from Jupiter. So my whole project then, I decided to center around Jupiter, and in the end I built a radio telescope to observe these signals. So before we go any further, we have to understand the electromagnetic spectrum. So any of you remember way back in high school, or maybe that was just like a year ago for you, I don't know, in physics class, learning about the electromagnetic spectrum. So this is radiation that permeates the entire universe. And we think of light as what we can see with our eyes, but really light can be anything from radio waves to gamma rays. So all of this, so light is really just electromagnetic radiation. And in astronomy, this is what telescopes are based all around, of course. So a visible light telescope will likely have a mirror or a lens to collect light, and then they'll maybe use a spectrograph to split that light up to analyze it further. But some telescopes are also based around other frequencies of light. So for example, like ultraviolet or infrared. So you might have heard about the James Space Telescope, James Webb Space Telescope recently. And that telescope has been built around infrared and visible light. And so the infrared, looking at the infrared in the universe is very useful when you want to study stuff that's super far away, or in other words, super old in the galaxy or in the universe, I mean, because of something that's called the Doppler effect. And so all of these galaxies and stars are getting essentially red shifted. So their light is becoming kind of more and more towards the red, and then it goes into the infrared. And this is because the universe is expanding. So what I was looking at in the electromagnetic spectrum, I was looking at radio frequency. So just like light, radio is a kind of light. And I was looking right at 20 megahertz. So your typical radio that you tune into in your car, you listen to just in your daily life, is around 80 megahertz to like 110 megahertz. So I was looking just below this at this frequency that Jupiter is kind of known to emit signals at. So I'll go to the next slide, actually. Initially, these radio signals from Jupiter were discovered back in 1955 by two radio astronomers in Washington. And they noticed these strange signals coming from the planet because they had this 96-acre array of radio telescopes or antennas set up to detect signals from space. And they started observing this kind of signal that would come fairly consistently. And so they take note of this signal. They observed it very carefully for several years. And they were able to attribute it to the side, or rather the face of Jupiter that was pointing towards Earth at the time of the signal being emitted. And so when we talk about really any planet, you can talk about the coordinate system. So just like on Earth, we have longitude and latitude. And there is, of course, the central or prime meridian, which passes through Greenwich on Earth. On Jupiter, there is also a central meridian. And this is just essentially what we call the y-axis, I guess. And this is your origin. So right here at the equator and the central meridian, that is where you'd have coordinates of 0. And so once you have a line of origin, you can plot, or you can split the surface up all the way into 360 degrees. And so this makes it a lot easier to keep track of what side of Jupiter is facing you at what time. And so they would initially do this by looking at the surface or at the clouds of Jupiter, and that was the best estimate that they had. However, the clouds on Jupiter, and of course many storms, they're all moving. So the rate at which the storms are moving around Jupiter is not the same rate that Jupiter is rotating. And this came up way later in their observations of the radio signals, because they noted, okay, so the central meridian would be at this point consistently when a signal was observed. But over the course of several years, they noticed that this signal was actually drifting. And so from this, they had to be like, okay, either our observations are incorrect and all we know about Jupiter's rotational period is incorrect, or their understanding of the rate at which Jupiter is rotating was wrong. And so it turned out to be the latter. So what they figured out from these radio signals, which turned out also to be polarized, and this is a key piece of information because this was indicative of the fact that Jupiter actually has a magnetic field. So knowing that Jupiter has a magnetic field, they were now able to use these radio signals to have a more accurate understanding of how long it takes Jupiter to rotate in one day. So now we know Jupiter takes 9 hours and 55 Earth minutes to complete one full rotation. So that is very fast. It's like more than twice as fast as the Earth. And so they couldn't use anything on the surface anymore, and it just, was not accurate. So how does Io come into play here? So going back to the Jupiter radio signals that were initially observed, they would see right when the central meridian was around 250 degrees, that was when these signals were always consistently observed at. However, that was not the only location that these signals appeared. So that was not the only reason behind these signals. They found out, more years of observing, that Jupiter's moon Io actually plays a key role in the probability of detecting these signals. So much so that it became a whole new area to study the relationship between Jupiter and Io. So understanding the Io phase is basically just like the coordinate system on Jupiter, understanding where Io is in its orbit. So the Io phase is just a measure of how far around Jupiter Io has come in its orbit. So 0 degrees is marked right when Io is behind Jupiter relative to Jupiter and the Earth. And then 90 degrees comes around here. So then this would be 180 degrees, and then 270 degrees, and then that 360 degrees or 0. So what was observed when they were looking at the relationship between Io and Jupiter was that they would always see these signals when Io was either at 90 degrees or 270 degrees. And so this was very curious. And so they started plotting these graphs where they'd compare the Io phase, so going from 0 to 360 degrees. So that's, again, how far Io is in its orbit around Jupiter. And then the central meridian longitude. So that is also 0 degrees to 360 degrees. So where that central meridian is in its rotation around Jupiter. And as they plotted the times they would see these signals at, when they knew the central meridian longitude and the Io phase, they started noticing these patterns. So you can see right around 250 degrees, if you look at the central meridian, then there are quite a few signals right here. So that is a significant pattern, and those were the signals that they used to understand Jupiter's rotational period. However, the Io phase provides a whole new kind of interesting pattern here. So looking here, the Io phase when it's at 90 degrees, and for this, the central meridian longitude actually doesn't play any part. But when Io is at 90 degrees, you see there's quite a higher probability of detection. And then again, up here around 270 degrees, there are two other sections here where it's more likely that you detect these signals. And so these locations of higher probability were categorized based off of their likelihood of detection. So IOA, you're most likely to detect. IOB, you're less likely to detect. And then IOC, you're even less likely to detect. So what I was looking at during my project, I was looking at Jupiter right when it was in this spot. And you'll see later on my software and everything, you'll see Jupiter is right in this spot. So that was the event that I was looking at. This is the antenna setup. So some of you might recognize this. This is Lansdowne Middle School. And I must have come to this field 5 or 6 times throughout the winter. And man, was it frustrating. So figuring out the software, all of the materials, and setting it up in the right position took many, many hours. Of course, in the end, worked out. Very glad. And so the antenna setup itself is very specific. So a dipole is a kind of antenna, and it basically focuses on the frequency at which, or rather the wavelength, they're related, at which you're observing. So because I was observing at 20 megahertz, or in other words, 20 million hertz, I could use this little equation, which relates the speed of light to the frequency to give you the wavelength. So taking the speed of light, being 300 million meters per second, very, very fast, and dividing it by the frequency of 20 megahertz or 20 million hertz, I can get the wavelength, which is 15 meters. And so I'm sorry to all of you metric fans, I did do most of my project in imperial because I was using many hardware store materials. But here it gives you an idea of the wavelength. So the wavelength of the frequency that I was looking at was 15 meters or 49 feet. So for the dipole to work, this length has to be exactly half the wavelength. And so I had 2 dipoles so that I could get double the signal, because these signals coming from Jupiter create like a millionth of a volt when they come in. So they're very, very weak. And so this across here is about 24.5 feet. However, the wire, this little copper wire, which is the actual antenna part, is not actually connected at the center here. Instead, it's connected to an insulator, a ceramic insulator. So these sections had to be cut to a quarter wavelength. And then, so right at the center here and on the ends, we have the insulator. And then the coaxial cable, which runs from down here all the way to the power combiner, which you cannot see in the grass, I'm sorry. This is connected. And then the coaxial cable is exactly 1 wavelength. However, if I were to put in just 1 wavelength in length for the coaxial cable, I'd lose a lot of the signal, because the signal, as it comes in from the waves, it's not traveling at the speed of light anymore as it's passing through the cable. So instead, I need to know about something called the velocity factor. And this is usually given as a % of the speed of light in vacuum. So for the coaxial cable that I was using, it was 66%. So I needed to multiply the wavelength by 0.66 to get the length of the coaxial cable, which worked out to be about 32 feet. Why am I telling you this? So in order for all of the signal to come in to my computer and be like fully there basically, and I actually have it all and I'm not losing signal, these two dipoles have to be in phase. So as a signal comes in from like way over here in the sky, this dipole would get hit before this one. So to do that, I had to add in some more coaxial cable over here so that they'd be in phase. They'd both be getting hit at the same time. And then from the power combiner, there would be a coaxial cable that would run to my computer, which is over here. And that is where I could actually see everything that was happening. So this is the software. This is what I would use to predict the IO events. So you might recognize this from a few slides ago. This is the plot of central meridian longitude versus the IO phase, and it gives me the areas of higher probability, and so I know when to go detect. And this is another part of the software. And here I can enter a specific time and date. So if I say I want to go observe next weekend at 8 a.m., I can enter that time and date into the software, and it will show me where Jupiter is and how probable it is that I'll detect something at that time. So this is really key. So I wasn't just going and setting up this big antenna and hoping for the best. So I actually knew when to go observe. And you might have noticed, I did, just for the purpose of this presentation, I actually entered almost the exact time right now. So you can see Jupiter is right up here. So Jupiter is below the horizon. That's where the blue line comes in. That means Jupiter is below the horizon. Can't do anything if it's below the horizon. But yeah, I was 3 minutes off with that. So close. This is what I was looking at while I was actually observing. So kind of looks scary. It was, as I was trying to configure it for months. But finally, I ended up with this program that acts as a spectrograph. So it takes the signal that comes in and it converts it into a plot of frequency on the y-axis versus time on the x-axis. And so you see there are a lot of horizontal lines here. So that is all local interference. And I did my best. I was out in the middle of an open field trying to mitigate the noise, background noise. But of course, being around buildings and being in town, there was inevitable interference. So this could be anything from power lines to HVAC systems. However, luckily for me, I knew about these IO emissions. They have very specific characteristics. So when they come in, they're very short little lines, and they span several megahertz. And they come in just almost like popcorn sometimes. And they come in very sporadically. And some of them can be wispy, some of them can be just very straight little lines. And they, for me at this time of observing, when I actually got the data, they came in over the course of about half an hour, which was perfect. And I got super excited, of course, when I finally saw this happening. However, I needed to figure out some way to confirm my findings. So luckily, oh, and yeah, so this is a result. This was one of the better images of the spectrograms at the time. So you can see here there's more wispy signal. And so in order to confirm my results, I put my results first up online at the Radio Jove project, and they have a big forum, so a whole bunch of other nerds that love this stuff, and they're just like dying to talk your ear off about it. So I knew that was a place, of course. And I put it up there. And I was like, I saw this signal at this time. I was observing the IOB event. Did anyone else see anything? And a few hours after I made the post, I had another member of the forum comment down below, and he was like, yes, I saw the same signals as you at the same time. And he was actually down in Mexico. So that was like really cool to have that confirmation. I can also rule out some other things. So at the time of observing, the sun was below the horizon, which is important because solar interference is definitely a problem. However, solar interference often looks way different, and it looks way more wispy, and it spans many more megahertz. So I could kind of rule that out. And of course, like I said before, I was doing all that I could to mitigate the noise. So that was the final result. Very happy about that. And now I'll talk about kind of the future of this project. So my end goal was, of course, to collect my own data and upload it to this website and the database, and be able to say, okay, this was an IOB event, so the professionals can then go and use it. I do not intend on stopping this at all. Oh my gosh, no. I would love to go maybe someday in like many decades, I'll have my own house and I'll have like a proper setup. So I might have to move far away. So just get out of the town to mitigate that radio noise again. I'm sure my parents will love that. So I've seen some other people doing this project too. They have proper setups. They'll have wooden posts, not just like flimsy PVC pipes. And they have computers running 24/7 to watch signals. So that's like my dream. Anyway. Before that, I would also like to try and observe solar emissions, because solar emissions are a lot more powerful, and you only need one dipole antenna to detect them. However, they are not very predictable. To some extent they are, but not so much. So maybe sometime when I actually have the time, I will go and set up and, who knows, hope for the best. So this is an example of solar emission. So you can see it's a lot brighter when you have the software configured properly. Yeah. So this project, of course, I did it for capstone. That went well. The night before the registration for Vancouver Island Regional Science Fair closed, I decided, why not? I have this project. I will sign up. And there definitely was a bit of nostalgia behind that, because I had done science fair at UVic when I was younger, and I was like, this is my last year of grade school and my last chance to go and do this. And so I was like, yeah, why not? I'll sign up. So glad I did. I showed up on the day kind of not knowing why I was there. I was like, I just have this project that I really enjoyed doing and stuff. And I remember I told my dad, I was like, what am I even doing here? But I just kind of took it with a grain of salt. I was like, I get to share something I'm interested in. And then that went really well, so well that I was able to go to Canada-wide Science Fair. And so the moral of this story is, if there are any parents in the crowd who have kids who are even have the remotest interest in science, please encourage them to sign up for Science Fair, just so they can have this experience. If they can, if they're really into it, they'll probably get here. It is amazing. So every year, every year, they hold Canada-wide Science Fair in a different city around Canada. And this year is Edmonton. Again, because UVic did their science fair so late in the season, they didn't know who would be going from Vancouver Island until like a few weeks before this actual event. So I didn't know I was going until a few weeks before this actual event. And having a whole week of May taken out of your grade 12 year is kind of scary, because I was studying for tests and exams. But of course, in the end, really glad I did this. So it was a week-long event in Edmonton, and we got to visit U of A. So I went, of course, to the Observatory there. And this was our team. So these were other kids from Vancouver Island. Me with my project. This was at the Science World in Edmonton, and we got to go into the planetarium there. And instead of doing like cool astronomy show, instead it was a Taylor Swift laser show, which honestly I'm not complaining. It was pretty cool. Yeah. And then the award ceremonies, but yeah, super great experience. And it all came from this kind of little passion project of mine. And I never would have thought that any of this would have happened from that. But yeah, again, moral of the story, please encourage your kids to do science, because it can lead to really fun things. Okay, that's it from me. So I'd love to take questions if you have any.
So are there any questions? It's my solemn duty to take the microphone around so that you all appear on the stream for posterity and all that kind of stuff. Brock.
Thanks for the talk, Evan. I'm just curious about, you were talking about the phasing of the two antennas. Is that do you have to determine where Jupiter's going to be when you want to, because you need to know that angle first, and then you tune the lengths? Is that essentially how it works?
Yes.
Sorry, I was too busy listening.
No worries. Yes, exactly. So I needed to know where Jupiter was going to be in the sky at the time of observing, and of course, too, for the setup of the actual antenna. So I can go back just to get that image. So I could choose either between like a 90-degree phasing or 180-degree phasing, and this kind of all depended on my latitude, and then of course where Jupiter was in the sky and in its orbit. So I landed on the 90-degree phasing because I was just within that range of, I think it's like 30 degrees of latitude to 50 degrees before you actually need the more serious phasing. But this still seemed to work out pretty well. So it turned out to be about 88 extra feet of coaxial cable that I just added on to the southern dipole. And so with that, because it was 1/4 wavelength, it was these fractions of the signal coming in, so there was no signal lost. And yeah, so again, I was just referring to the website and asking around people who had done this project, like what the best kind of degree of phasing would be. Lands on 90 degrees, seemed to work out. Yeah.
When you said that, like, what's the word? You were going to have like a proper set and you're like going to watch it 24/7 with like a computer. How would you catch all the data on to like something where like the people who like look at it and like do stuff with it to figure stuff out with it, like the science, other kind of science people? Like, how would you capture all of it? Like, how would you capture it all onto like one piece of program? Like, how would you capture all of it?
Great question. Yeah. So I think I know what some other amateurs have done is they just write a bit of code, which I know nothing about, so don't ask me about that. They write a bit of code, which basically just monitors the programs that they're looking at. So again, like this screen basically monitors a spectrograph. And so when there's a bigger disturbance, so a bigger kind of like either IO-related event or non-IO-related event, it'll pick up on that. And either the computer will start recording then, because this is just the incoming signal. There's actually another function to start recording. So, oh wait, hang on. No, this is actually recording. I was recording this time. But you can have the signal coming in and not record it. So if you have some code to monitor this, and it will detect when there's a signal, it'll just start recording and stop recording, so you don't end up with gigabytes and gigabytes of data. Yeah. Yeah, essentially, yeah.
Can you actually tell whether it's coming from Io or Jupiter?
Yes, so I had lots of other emissions that people had uploaded to go against or to go compare with. So I studied the characteristics. I could tell with the very specific, like, popcorn kind of style emissions coming in. And then, of course, the confirmation with the gentleman down in Mexico was like my biggest help, because again, I was new to this project and I was able to compare with his exact spectrogram and see how it lined up and everything. And we also had some input from other professionals on the forum who helped out. I don't know if they were detecting at the time, but they have had years of experience with this because they started the whole project.
You mentioned about solar radiation interfering with what you can detect or what you're looking for. I think Jupiter takes 12 Earth years to rotate around the sun. Is that about right? And so is there a time of year when you couldn't have observed these signals because the sun would have been in between you and Jupiter? And were you lucky that you were observing at the time of year you were?
Yes, absolutely. So I was very lucky because just last year, Jupiter came kind of the closest to us that it has been in a long time in its orbit and our orbit. So it was way past, like way out on the other side of the sun, basically. So we were looking out kind of from the sun towards Jupiter. But yeah, so if Jupiter was all the way around on the other side of the sun, it would make it a lot more difficult to observe that directly. Yeah.
It's called opposition.
My question is about the software. Now, where did you get it on the forum or from the forum? Like, sorry.
I decided not to lunge anymore.
Yeah, so another great question. Like I said, I don't have any coding experience or anything, so I definitely could not have created all this. This just came from the other amateurs who were also participating in this project. And there were many different packages of software that I downloaded for this. Some of them worked, some of them didn't. The ultimate issue for me was that I was using Windows 11 of all things. Anyway, I won't go into that. I had like a 60 email long exchange with someone just on that. So that was an issue. But yeah, this was all suggested and verified by other people who were also doing this project and advertised all over the website and everything. So yeah.
Got time for another couple here?
So I saw something about volcano. So Jupiter's radio waves are coming for many reasons, of which you mentioned volcano in your.
Yeah.
So could you isolate or point out in your results what were different sources based on where they were?
Yeah, so thank you. Like I mentioned before, I need questions because I might have missed stuff, and I did miss that. So volcanoes, yeah, that actually played a role in the theory behind it all. So Io is the most volcanically active body in the solar system, and as a result, it is emitting lots of material out into its atmosphere, like every second, mostly sulfur compounds. And so a small fraction of that actually escapes into space and consequently becomes ionized. So it loses its electrons, and then these charged particles get trapped in Jupiter's magnetic field. And then they start kind of following Io in its orbit. So it creates kind of like a torus around Jupiter. So it's called the Io torus. And so this torus of charged particles is stuck there. And then as Jupiter rotates super quickly, its magnetic field moves past these charged particles. And so if you remember from physics class, a conductor moving through a magnetic field creates a current. And so because Io has a very thin conducting atmosphere, it's moving through this magnetic field, and these particles are these charged particles are what are thought to create the signals, but we don't know exactly like where it's coming from, and it's not a perfect circuit. It's more like Io creates a bit of a disturbance in the magnetic field, and then that disturbance is what creates the signals. But we know, for example, if this is actually related or not related to the Io versus non-Io related emissions. It's a lot of related. So that's the question that like we're still asking. We're also asking questions about like how dense this Io torus is, and like for example, Jupiter has lots of other moons, and why is it only Io that creates this phenomenon? Are there other moons that play a part here? Does the sun happen to have anything to do with these emissions? So yeah, lots of unanswered questions still.
Okay, I'll take one more. Here you go.
Great, thank you. Mine's about the hardware and the antenna setup. How many times did you set it up? How long did you leave it up for? How precise did you have to be in the distance that each piece was?
Yeah, so going back to this, I went and set this up, like I said, 5 or 6 times throughout the winter. Again, because Io had to be in the right position, so that was only every couple of weeks. And I would set up for 3 or 4 hours, depending on the day and the time. And most of that time was spent configuring the software, because a lot of the software, could not actually be configured and set up unless it was connected to the antenna, and I could like verify that it was receiving at least something from the setup. In terms of precision, I had a good like 6-inch, plus or minus 6 inches in terms of like the length of the wires and the length of coaxial cable. Because again, I wasn't looking directly at the 20 megahertz frequency. It was more around that frequency. So between like 10 and 40 megahertz. It's just I had selected that frequency because it's known that the signals are most likely to kind of come around that frequency. So that is what I selected for the actual physical setup. But yeah, like you could see on the spectrograph here, I'm looking between 16 megahertz and 24 megahertz, so right around 20. Yeah.
Well, thank you very much for that. Great piece of experimental science, and shows how easy you can get going on something that produces real data. So thank you very much. If you want to hear this again, where I have to give Evan a break. He has to give the same presentation at 9. But if you want to see it again, it'll be live on YouTube, and also not live on YouTube. Thank you. We have tours of the dome starting at 9 o'clock, which we're giving Evan the night off for. And also at 10, if there's anything to see in the sky with all the smoke and haze, we will attempt to image deep sky objects with the Plesket telescope. So if you can stay around that long, that's where to head.
Hi everyone, welcome to What's Up in the Sky for August 19th, 2023. Be sure to check out our gift shop in person or online. And we're grateful for your purchases there, which helps support our educational programs, and also for your memberships and donations, which clearly support our educational programs as well. And note that we have summer daytime hours still, so stop by and say hi, and we'll be doing dome tours and planetarium shows throughout the day. And the summer daytime hours continue until September 29th, and they're Tuesday to Friday from 10 a.m. to 3 p.m. And note that we're Saturdays in the daytime. There is an admission price because we need to raise money for our educational programs, and the seniors price is, and that's for people who are 65 and over, is $12. For adults age 18 to 64, it's $15. Students age 18 to 25 with valid student ID is $8. Youth age 7 to 17 is also $8. And children 6 and under are free. And it's also free for the Wasonic community as the observatory resides on their traditional territory. Now, as for sunset, twilight, and sunrise, sunset was at 8:20 p.m. at 20 degrees north of due west in azimuth, and sunrise was at 6:12 a.m., rising 20 degrees north of east in azimuth. And the sun was at its highest point at 1:17 p.m. at 54 degrees above the southern horizon, and it's actually already 6 degrees lower than when I last did this at the end of July. And astronomical twilight ends at 11:23 tonight and begins at 4:06 a.m. So we're starting to get more hours of darkness here. And the new moon was a few days ago on August 16th, and the current moon phase is a waxing crescent of about 10%, meaning it is getting more full. And this is an excellent time to watch how the phase changes from night to night with a small telescope as the moon moves towards full. And in particular, you'll see shadows from the mountains and shadows inside of craters, even with a small telescope. So I tried watching the Perseid meteor shower from what could have been an ideal location, the Columbia ice fields, a few days before the peak when the moon had not yet risen. And I did see a bright meteor over the Athabasca Glacier, a very memorable sight. However, while it was technically clear that night, fire smoke dimmed the view, and I could only make out as many stars as I could see from home near the Hillside Shopping Center here in Victoria. And the Columbia ice fields is considered to be one of the least light polluted areas around, and ranks as a 1 on the Bortle scale of light pollution as a result. And I can just actually show a little map here to actually show this area on a really cool map that's created from satellites. And here you can see Edmonton is really bright over here, and Calgary is bright over here. And this is the brightness level represents the amount of light pollution. And if you look down here, you can see a spot for Banff National Park, Lake Louise, and this is Jasper up here. So there is some light pollution from those areas. And the spot that I was located in, that my wife and I were located in along with some friends, was right about in the middle here. And if you're just to sort of click in that area, let me see if I can zoom in a little bit more. And so say around here, and you should see, okay, so it says class 1 for the Bortle level, and it also gives a brightness in magnitudes per square arc second in the sky. And so that I actually clicked it pretty close to where we were. There's Mount Athabasca right there. So this is a really cool tool for just educating yourself about light pollution around the world and where some of the least light polluted areas are. And so if you look up at the URL here, you can see it's simply lightpollutionmap.info, and then you can go from there. So I'm just going to stop sharing here for a second. Okay, and we might come back to that in a few minutes. And on our flight back from Winnipeg a week later, I noticed that there was fire smoke in all of the valleys in BC that I could see from the plane from about 35,000 feet. And we all know the wildfires are a catastrophic situation here in our province, and it's now even starting to affect our view of the stars. So why is that? The fire smoke particles are similar in size to interstellar dust particles, and so when astronomers look at the stars through that interstellar dust, we call it reddening, for exactly the same reason the sun looks red when setting. And red light can make it through the dust. It is longer wavelength, but shorter wavelength blue light gets scattered away. And I'm going to show a couple of photos relevant to this, if I can get them up here. So this is a shot that I took at the observatory last September. So this is about a year ago. And you can see the setting sun through some fire smoke. And certainly there's even some red light being scattered around, but the sun is definitely red there. And if I just click on next here and click on this, this is an image of a dark cloud of dust in interstellar space. And if you look along the edges here, you can see that in fact the stars that are in the background are noticeably red. And so this is this is not in our atmosphere. This is way off in space, and yet it's the same kind of effects. So we're actually dealing with that. And there's also it also dims the light, as you can see from this photograph, and as you can tell from that photo of the setting sun. And there's an even perhaps more appropriate name for that effect, and it's called extinction, because in astronomy it extinguishes the light. And I think perhaps here on Earth it might have a double meaning now. So that's food for thought as we look at the fire smoke, or look through the fire smoke. So the number of stars that we see and our view of the Milky Way through fire smoke is simply not as good as it would be without it. So let's just talk a little bit about what's up in the sky, change subject a little here, and have a look at stellarium. So I'm going to share stellarium here. And so Venus and Mars are now gone from the evening skies, and Saturn rises in the east at 8:37 p.m. You can see the time here is 8:56 on the clock that I have set in stellarium. And so Saturn is just up over sort of the southeast in the sky. And it's going to be well placed as the evening goes on, and it's rapidly becoming the feature object of late August skies. And it's a great target, as many of you know, even for small telescopes. And Jupiter also rises in the east, and it rises at about just after 10 p.m. So I'm just going to advance the clock here and move this over. And you can see Jupiter coming up just a little bit north of east there in the sky. And so, so I should also just talk a little bit about something else that's up in the sky. And I'm going to stop sharing here again. And while camping near Jasper on Friday, August 4th, I wondered why the twilight seemed to be lingering, because I was expecting it to be a pretty dark sky. And I thought, well, is this city lights or what's going on? And I soon realized that the sky was moving, and I was observing the northern lights. And I'm going to just show a couple of images here of that I took that night. Hopefully they look okay. Probably come up with the Barnard object first, but that's not it. Let's just move around here. And actually, I'm going to close this up. Okay, try this again. All right, just bear with me as I bring this up on the screen. Always have to have a few little technical difficulties in this talk. All right, and so here is the first photograph that I took of the Northern Lights, and so it was actually quite colorful, and there were streamers in it, and you can see that there's several different colors visible. And here's another view I took a few minutes later of it, and you can see it has a bit of a purpley color. And you might be wondering what's going on with the red foreground. Well, it turns out that unfortunately, even though this was in a national park campsite, they had a bright street light there, and so that was illuminating the ground. And here's a shot overhead, give you an idea of what we're seeing. It kind of looks a little bit like clouds, but in fact, that was the aurora, and it was moving the whole time that I was taking these pictures. So the pictures are actually a little bit blurrier than what I saw with my eye, simply because it was actually moving around during the time exposure. And so what was going on was that a solar flare had happened a day or two earlier, and it was crashing into the Earth's upper atmosphere, producing little flashes of light. And so it was compressing the Earth's magnetic field at the same time, and we're able to see the aurora a little bit further south. And this was certainly the most spectacular display that I'd ever seen in my life. And I was really also just fortunate that the fire smoke had abated that day, and so I was able to see it. And so a colleague told me yesterday that seeing the Northern Lights was on his bucket list. And in fact, you can see them from Victoria, but you have to know when to look, and you also need to get away from city lights. And so I actually recommend going to a website, which if you listen to these things regularly, you'll know is called spaceweather.com. And I'm going to see if I can bring it up here if I haven't closed the window. And just bring this up. Bear with me for another second or two. And here we go. So this is the spaceweather.com site, and if you look down the left-hand side of this website, you'll see something that says current auroral oval. And when that is actually down over top of Vancouver Island, that's an excellent time to look for it. And that usually corresponds to something where the KP index is 5 or higher. If it's around 7, then the aurora oval will be further south and probably covering Vancouver Island. So go to this site for predictions about the Northern Lights as we get further into the solar maximum over the next year, and I think you'll stand a pretty good chance of seeing them from Vancouver Island. So let's just talk a little bit about the summer constellations now. The next few days should be an excellent time to explore the summer Milky Way, assuming there's no fire smoke. And you'll also have to be as far away from city lights as possible. And the last time I did one of these sessions at the end of July, I encourage everyone to get to know the constellations and asterisms of the Milky Way. And remember, asterisms are not formal constellations. They're just little figures we connect, such as the summer triangle. And I suggested starting with Scorpius. We're going to go back to our sky map here and in Stellarium. And I'm going to put the constellations up here just to help us get oriented. And so currently here, we're almost at the end of astronomical twilight. I'll just make it around the end. And there you can see that Sagittarius is visible and Scorpius is actually just setting there. So if you want to see Scorpius, you have to look a little bit earlier in the evening during astronomical twilight. But you can see the Milky Way rising up straight up out of the horizon. And so, and if possible, you want to be not only away from city lights, but make sure there's no city lights to the south of you in particular. And so the waterfront southwest of Victoria is an excellent place to observe these areas of the Milky Way from. So that's anywhere from sort of a Esquimalt area, but having the lights at your back, off to Souk and further to the west from there. So there's some excellent views of the southern parts of the Milky Way to be had from there. And so I also recommend that you try to identify the constellations that I was just referring to that are part of an asterism known as the Summer Triangle, which is Vega, Deneb, and Altair. And this is one of the richest areas of the Milky Way, and it's right overhead at this time of night, just after about 11:20 or so at night. And so it kind of maximizes your view of the faint stars in the Milky Way. And Cygnus the Swan is a typical Western name for this. And if we flip the constellations on here, you can see a depiction of a swan. But in Stellarium, you can actually go to the Star Lore tab and pick other folklore, and you can see that in fact it's actually known as a crane. So it's actually a different bird. So that's kind of cool. And I guess other people just thought that, hey, those look like wings outstretched in the sky. So I encourage you to experiment with different constellation depictions in Stellarium, and it's a free program. You can it runs on the Mac and also PCs. So notably, also this area of sky, whether you call it a crane or a swan, is an area where planets have been found, and that's where the Kepler Space Telescope looked for planets. And currently, the count of confirmed planets is at 2,398. And if you flip on this little planet button here, you can see where they're all located there in the Summer Triangle. And it's not that that's where most of the planets are in the sky. This is just where the telescope happened to look. So in any case, I encourage you to keep exploring the nighttime sky, and I hope you get smoke-free, for everybody's sake, smoke-free skies and enjoy this hobby. So thank you, and as always, keep looking up.